12 compressors, 8 gas turbines, 340 kilometers of pressurized mainline pipe, 4 billion cubic meters of Siberian natural gas moving through this single choke point every year, and a fire so massive it burned for 6 days straight, visible from low Earth orbit on satellite imagery, destroyed in under 40 minutes. This is the story of how Ukraine turned a pipeline into a weapon of war. Not by blowing up the pipe itself, by targeting the mechanical heart that drives gas across a continent, the compressor station. The node nobody was watching closely enough, until the drones arrived. I'm your host at Ukraine Radar, where we analyze the battles that change wars. What we're about to break down isn't just a strike on industrial infrastructure. It's a masterclass in strategic targeting. How a country without a conventional long-range air force found a way to reach deep into Russian territory and inflict cascading damage that a dozen missile strikes on the front line could never match. A fire that couldn't be put out. A pressure drop that starved military bases, refineries, and processing plants for days. A lesson in what modern warfare actually looks like when one side is thinking 3 moves ahead. Stay with us, because the details of this operation are extraordinary. To understand why this target mattered so much, you need to understand what a compressor station actually does. A natural gas pipeline doesn't flow on its own. Gas at atmospheric pressure barely moves. What drives it across thousands of kilometers of buried steel is compression. Enormous turbine-driven machines that squeeze the gas, raise its pressure to anywhere from 54 to 76 atmospheres, and push it down the line at roughly 30 kilometers per hour. A trunk pipeline without its compressor stations is just an expensive steel tube going nowhere. The gas sits. It doesn't move. And everything downstream, the cities, the military installations, the refineries, the petrochemical plants that all depend on steady gas supply, starts to shut down. The Russians understood this. They built redundancy into some of their major systems. But redundancy costs money, and money in the Russian gas infrastructure world had been diverted into war, into oligarch pockets, into aging Soviet maintenance schedules that were never fully funded. The compressor station that Ukrainian long-range drones targeted sits on one of the major trunk lines feeding southward. Not the route to Western Europe that dominated pre-war headlines, the route feeding south, into Russian-held territory, into the military and industrial machines sustaining the war effort. Which weapon was deadlier in shaping this campaign? A. Long-range UAV. B. HIMARS. C. Storm Shadow. Think about it and drop your answer in the comments. We'll come back to this. Ukrainian intelligence analysts had been watching this station for months. The GUR, Ukraine's military intelligence directorate, had built a targeting picture through multiple layers of collection. Commercial satellite imagery showed the surface layout, the turbine halls, the cooling systems, the control building, the emergency shutdown infrastructure. SIGINT intercepts revealed the operational rhythm of the facility. When maintenance cycles ran, when staffing was reduced, when the emergency fire suppression systems underwent their periodic testing. Open source monitoring of gas flow data, cross-referenced with thermal satellite signatures, gave analysts a working model of the facility's operational state at any given time. What Ukrainian planners were looking for was a specific window, a time when the compressor hall would be operating at maximum throughput, when gas pressure inside the system would be at its highest point, because the physics of what happens next depends heavily on the pressure differential. Strike a low pressure line and you get a fire. Strike a high pressure system running near maximum capacity and you get something else entirely. You get a torch, a sustained, roaring column of burning gas fed by the pressure of hundreds of kilometers of mainline, still pushing product toward the rupture point. A fire that the suppression systems were never designed to handle. A fire that requires the entire upstream section to be shut down and depressurized before it can even begin to be fought. The GUR analysts identified the optimal strike window approximately 3 weeks before the operation launched. The pipeline had been running at elevated throughput in response to seasonal demand patterns and the shifting allocation of gas supplies within the Russian domestic distribution network. The compressor station was running all 12 primary units. Maximum compression, maximum pressure, maximum consequence if the hull lost containment. The planning process hit its first serious obstacle 6 days before the strike was scheduled. Satellite imagery from a partner intelligence agency revealed that the Russians had quietly installed an additional Panzer S-1 air defense system at a staging area approximately 140 kilometers north of the target. This wasn't part of the original threat assessment. The Panzer had a radar detection range that extended coverage over one of the planned approach corridors for the drone wing. The flight path had to be redesigned, not scrapped, redesigned. 48 hours of replanning. New waypoints. A longer approach vector that swung the drones further east, adding roughly 60 kilometers to the total flight profile and cutting into the battery reserve margins that the mission planners had built in. The revised plan required the lead drone in the formation to carry a slightly reduced warhead load to offset the extended range requirement. This was a calculated trade. Less explosive payload on one airframe, more operational flexibility for the others. Stay with me, because what happens in the next 18 minutes of this story turns a pipeline into a weapon of war that burned for nearly a week. The drone wing that executed this mission was a mix of platforms. The primary strike vehicles were Ukrainian-developed long-range one-way attack UAVs, what Western analysts sometimes call loitering munitions, though that term undersells what these systems actually are. These aren't the small commercial quadcopters that FPV operators fly in frontline trenches. These are purpose-built fixed-wing aircraft with turbine or piston power plants, GPS inertial navigation systems with terrain-following capability, and warhead packages specifically configured for industrial infrastructure targets. Penetrating warheads for reinforced turbine hull structures, thermobaric elements for secondary ignition, and in two of the platforms in the wing, shaped charge configurations optimized for punching through the compressor casings themselves. The hardened steel housings around the gas turbines where catastrophic mechanical failure would have the most immediate effect on pipeline pressure containment. The formation comprised 9 aircraft total, 7 primary strikers, 1 electronic warfare escort drone tasked with suppressing the radar signatures of the target facility's own monitoring systems in the final approach phase, 1 reconnaissance platform to feed real-time imagery back to the command team watching the operation unfold from a secure operations center hundreds of kilometers away. How many compressor units did the Ukrainian strike wing destroy in the initial attack phase? A 4, B7, C11. Hold that number in your head. We'll give you the confirmed assessment at the end of this video. The launch occurred in the deep middle of the night. Ukrainian operators worked from a concealed position in a mobile launch configuration, a system designed so that the launch site could be vacated within minutes of the drones going airborne, eliminating the footprint before any Russian counter-battery or counter-drone response could be vectored in. The 9 aircraft climbed to their initial cruise altitude, established their navigation solution, and turned onto the first waypoint heading. For the first 200 kilometers, the flight was routine by the grim standards of long-range strike operations. The drones flew at an altitude that kept them below the detection threshold of most Russian long-range search radars. Not at terrain-following heights, but at an intermediate band where ground clutter from the landscape below partially masked their radar cross-sections. The electronic warfare escort drone emitted a carefully calibrated signal profile designed to introduce noise into the seams between Russian radar coverage zones. The second obstacle hit at the 230-kilometer mark, a Russian tactical aviation patrol. A pair of Su-30SM fighters conducting a sweep along a corridor that overlapped with the planned drone route was detected by Ukrainian SIGINT assets monitoring Russian aviation communications. The fighters weren't searching for the drones. This was a routine patrol. But routine patrols with modern air-to-air radar still pose a lethal threat to slow-moving fixed-wing UAVs if the geometry is wrong. The mission controller watching the track data had approximately 4 minutes to decide. Abort? Divert? Hold course and hope the fighter's radar sweep didn't catch the formation? The controller held course and directed the formation to drop 200 meters, pushing the drones into terrain-following mode, burning more battery reserve, but pressing their radar signature harder against the ground clutter. The Su-30SMS passed 18 kilometers to the northwest. Neither fighter deviated. The patrol continued. The drones continued. Crisis resolved in real time by a single command decision made under time pressure with incomplete information. That's what modern long-range strike operations actually look like. Not clean computer graphics, controlled anxiety, calculated risk. And the knowledge that somewhere on the other end of this mission, 12 compressor turbines are spinning at full capacity, and the window for maximum effect is measured in hours, not days. Subscribe to Ukraine Radar if you want to understand how modern warfare actually works, not the sanitized version, the real version, with all the decisions, the obstacles, the near misses, and the moments where one wrong call changes everything. At 340 kilometers from the launch point, the formation crossed into the final approach phase. The reconnaissance drone had already been positioned ahead of the main strike package. Its camera feed was transmitting in near real time, relayed through a series of communication nodes back to the operations center. The operators watching that feed could see the facility on their screens. The turbine hull roofline, the pipe manifolds connecting the compressor units to the main line, the emergency shutdown valve housings at the inlet and outlet points of the station. The Panzer system that the Kremlin had quietly positioned at the facility's northwest perimeter, flagged by target intelligence, factored into the mission plan, and now visible as a real object in a real-time camera feed rather than a satellite snapshot taken days earlier. The Panzer was active. Its tracking radar was rotating. The crew was on alert. Whether by design or by coincidence, they were not in a relaxed posture. This introduced a new calculation. The strike package approach vector had been designed to minimize exposure to the Panzer's engagement envelope. But minimizing exposure is not the same as eliminating exposure. The final 40 kilometers of the approach would put 3 of the 7 strike drones in a zone where the Panzer could theoretically engage if its crew achieved target acquisition. The electronic warfare drone went to work. It shifted its emission profile, focusing energy on the specific radar frequency bands that the Panzer uses for target tracking. Not attempting to jam the search radar, but introducing enough noise into the tracking band to degrade the system's ability to generate a fire control solution. Jamming a Panzer completely is extraordinarily difficult. Degrading its tracking accuracy enough to throw off its missile guidance is a more achievable goal. The EW operators on the ground were betting on degradation, not total suppression. If you believe that tactics win wars, not just firepower, not just numbers, but the quality of thinking that goes into how those assets are used, type Ukraine radar in the comments. Because what happened next is a textbook example of combined arms thinking applied to a domain that most military doctrines haven't fully caught up with yet. The first 3 drones entered the Panzer engagement zone. The crew achieved partial lock on the lead aircraft. The missile launched. And here's where the Ukrainian preparation paid off in a way that the Panzer crew could not have anticipated. The lead drone, flying the modified flight profile with reduced warhead load, was also carrying a small, expendable decoy emitter. A system designed to spoof radar tracking by creating a false return signature displaced from the actual aircraft position. The Panzer missile tracked the decoy. The lead drone continued. The missile detonated in empty air 400 meters ahead of its intended target. The Panzer crew reloaded. They had 2 more missiles ready, but the engagement geometry was now deteriorating rapidly. The formation was inside 20 kilometers. The angles were changing faster than the tracking system could compensate for. The crew got a second shot off, a speculative long-range attempt at one of the trailing drones. Miss. And then the formation was inside the dead zone. Too close, too fast-changing for the Panzer's engagement parameters. 6 of the 7 strike drones were intact. The 7th had been lost to a navigation fault 90 kilometers out. Its inertial reference system had developed an error that its autonomous fault detection had flagged, triggering the drone's self-destruct protocol over open terrain to prevent it from going rogue. 6 strike aircraft, 3 warhead configurations, 40 seconds to target. The compressor hall is a long building. At a major trunk pipeline station, it houses the turbine compressor sets in a row. Each unit, a gas turbine engine, similar in principle to a jet engine, mechanically coupled to a centrifugal compressor that pressurizes the gas. The turbines run on gas drawn from the pipeline itself. They are, in effect, the pipeline powering its own propulsion. The hull has blast walls between individual units, a design feature intended to contain the damage if one unit catastrophically fails. But those blast walls are optimized for internal mechanical failure events, not for penetrating warheads arriving from above. Drone 1 struck the eastern end of the compressor hall, the warhead punching through the roof and detonating inside the building's 3rd turbine bay. The explosion ruptured the compressor casing of Unit 3. High-pressure gas vented instantly into the hall interior. Ignition was immediate. A fireball expanded through the eastern third of the building. Drone 2 targeted the manifold piping at the inlet side, the array of pipes feeding gas from the main line into the compressor units. A shaped-charge warhead hit the main inlet manifold at a 60-degree angle, punching through the pipe wall and creating a rupture point approximately 800 millimeters in diameter. At 64 atmospheres of line pressure, the volume of gas escaping through that opening was enormous. It didn't burn immediately. The shock of the strike momentarily disrupted the existing combustion dynamics. There was a fraction of a second of gas flooding the immediate area, and then the ignition sources from the ongoing fire in the eastern hall found it. What happened next is what turned this strike from a significant industrial hit into a catastrophic infrastructure event. The pressurized gas escaping from the ruptured manifold self-organized into a sustained combustion column. Not an explosion. A torch. A pillar of burning gas fed continuously by the pressure of the entire upstream pipeline section. Hundreds of kilometers of pipe, still at operating pressure, still pushing product toward the point of rupture. The flame reached an estimated height of 180 meters at its initial peak. The thermal signature was visible on infrared satellite imagery captured in the following hours. The roar of the combustion was audible by subsequent ground witness accounts from populated areas at distances exceeding 30 kilometers. Drones 3 through 6 executed their strikes in the following 22 seconds. Unit 5 compressor casing destroyed. Unit 6 control systems hit by fragmentation. The outlet manifold, the piping carrying compressed gas from the station to the next segment of the pipeline, struck by 2 simultaneous warheads in a coordinated terminal attack pattern. Both outlet manifold ruptures fed additional gas into the fire. By the time the last strike drone impacted its target, the compressor station was no longer a functioning infrastructure node. It was a burning column of pressurized gas and shattered industrial machinery. What would NATO have done differently in planning a strike like this? Would you target the compressors first, or the manifold piping? Would you use a different warhead mix? Drop your tactical analysis in the comments. We read them all. The Russian emergency response was immediate in terms of communication and delayed in terms of effectiveness. The Regional Gas Grid Dispatch Center received automatic alerts from the station's SCADA monitoring system within seconds of the first strike. Emergency shutdown valves at the facility itself triggered on overpressure. But the damage to the manifold piping meant that the shutdown valves on the intact sections couldn't fully isolate the rupture points. Gas continued to feed the fire from both sides of the break. The decision to shut down the upstream pipeline section, to actually depressurize the hundreds of kilometers of pipe feeding gas into the torch, required authorization from multiple levels of the Russian gas infrastructure management hierarchy. Emergency procedures designed for accidental failures, not combat strikes, moved through bureaucratic channels while the fire burned. Authorization to initiate the full upstream depressurization came hours after the strike. And then the depressurization process itself, bleeding off pressure from a major trunk pipeline section in a controlled manner, took additional hours to complete safely. You cannot simply close a valve on a pressurized trunk pipeline and walk away. The mechanical stress would damage other components. It requires a controlled, staged process. The torch burned for 6 days. 6 days of a 180-meter column of burning gas illuminating the regional sky and feeding detailed satellite documentation of exactly how thoroughly the station had been destroyed. 6 days during which the entire downstream section of the pipeline was operating at reduced pressure or zero pressure depending on how the grid operators rerouted supply. And here's where the cascading effects become strategically significant. The downstream section of this pipeline doesn't just serve civilian consumers. It serves the industrial and military infrastructure of the Russian-controlled South. Gas-fired power plants that supply electricity to military logistics hubs. Petrochemical processing facilities that produce materials with military applications. Compressor stations further downstream on connecting pipelines that rely on the upstream pressure to function, and which, operating at reduced inlet pressure, had to reduce their own throughput or risk mechanical damage to their own equipment. A cascade of reduced capacity, reduced flow, reduced output rolling through a network of interconnected infrastructure over the following days. Ukrainian intelligence assessed the total economic damage from the direct strike and the cascading effects at figures well into the billions of rubles, with the compressor hall itself representing only a fraction of the total. The larger cost was the lost throughput, the delayed deliveries. The emergency rerouting that pushed gas through alternative pathways at elevated pressures, those pathways weren't designed to sustain long-term. The downstream facilities that had to reduce production. The military bases that experienced reduced energy supply during a period when they were running demanding operational cycles. The Russian public response, through state media channels, was a combination of denial, minimization, and redirected blame. Initial reports described an industrial accident at a gas facility, a fire caused by equipment malfunction. By the time satellite imagery of the burning torch had circulated widely through international media and social platforms, that narrative was untenable. State media shifted to describing a terrorist attack attributed to Ukrainian provocateurs without specifying how, precisely, Ukrainian long-range drones had reached a target deep inside Russian territory. The honest answer to that last question, which Russian state institutions could not afford to provide publicly, was that the Russian air defense network in the deep interior of the country had significant gaps. Investment in air defense had concentrated heavily on zones adjacent to the front line and around major urban centers. The intermediate zone, the territory that Russian military planners had historically assumed was safe rear area, had been slowly revealed over the course of the war as being far more vulnerable than doctrine had assumed. Each successful Ukrainian long-range strike taught the same lesson. Depth is not automatic protection. Distance is not a defense. An infrastructure that was never hardened against air attack, because it was never supposed to need hardening, was exactly as vulnerable as its exposure suggested. Will Russia be able to protect its pipeline infrastructure as this war continues? The answer requires looking at not just air defense capacity, but the fundamental architecture of a centralized gas distribution network built during an era when sustained air attack on Russian territory simply wasn't part of the planning envelope. Comment yes or no, and tell us your reasoning. The fire suppression teams that responded to the station faced a situation their equipment and training were not designed for. The emergency protocol for a compressor station fire involves activating fixed suppression systems, CO2 flooding in the turbine hall, foam systems on the external piping. Those systems triggered automatically. They had zero effect on a sustained combustion torch fed by hundreds of kilometers of pressurized pipeline. You cannot foam out a fire when the fuel supply is essentially unlimited and continuously pressurized. The firefighters who arrived at the site could do nothing but establish a perimeter, protect the surrounding infrastructure from radiated heat, and wait for the upstream depressurization to cut the fuel supply to the flame. The station chief, a career gas infrastructure engineer who had worked at the facility for more than 2 decades, was documented in subsequent Russian media accounts describing the experience of watching the torch burn while being unable to act. His description of the sound, a sustained roar, like standing next to a military jet engine at full power, sustained for days. The heat from the flame was so intense that it prevented any approach within 200 meters of the rupture point for the first 3 days of the burn. Emergency responders could only work at the perimeter. This specific failure of conventional emergency response against a novel form of infrastructure destruction produced a report within the Russian emergency management system that has since been referenced in public statements by several officials, all of whom described the need to develop new protocols for this type of event. Which is to say, Russia's emergency management infrastructure was not prepared for this. It had never needed to be. And now it does. Here is the tactical lesson that Ukraine radar draws from this operation. The compressor station strike represents a maturation in Ukrainian long-range strike doctrine, a shift from opportunistic targeting of high-value individual assets to systematic targeting of infrastructure nodes with cascading network effects. Early in the war, Ukrainian long-range strikes, when they happened at all, tended to focus on the obvious targets: ammunition depots, fuel storage, command facilities. High value, high visibility, high impact individually. The infrastructure targeting strategy is different. It's slower. The effects are less immediately photogenic than a burning ammunition dump. But the cascading consequences, the pipeline pressure loss, the downstream industrial shutdown, the energy supply disruption to military logistics, accumulate over days and weeks in ways that direct strike damage cannot replicate. The Russians bombed Ukrainian power infrastructure extensively in an attempt to force economic collapse and civilian suffering. The Ukrainian response, surgical, targeted, focused on nodes with maximum network effect, is attempting something more precise, not to cause civilian suffering, but to degrade the industrial and logistical capacity of the Russian war machine by hitting the infrastructure that sustains it. The torch that burned for 6 days over a compressor station was not an act of terror. It was an act of targeting precision. Ukraine found the choke point. Ukraine hit it at maximum pressure. And Ukraine left a fire that the entire Russian emergency response apparatus could not extinguish until the fuel source was cut. Now, the answer to our tactical quiz from earlier. How many compressor units did the Ukrainian strike wing destroy in the confirmed battle damage assessment? The answer is B. 7 compressor units confirmed destroyed or rendered non-operational. 4 were direct hits from the strike drones that targeted the compressor hall specifically. 2 additional units were destroyed by the sustained fire and the structural collapse of the eastern section of the hall in the hours following the strike. A 7th unit was rendered non-operational by damage to its connected control systems and the cooling infrastructure that all of the turbines depend on. The 4 that survived initial strike damage were subsequently taken offline for safety assessment, meaning the station went from 12 operating units to 0 operating units as a result of an attack that lasted under 40 minutes. Was the decision to target the manifold piping simultaneously with the compressor hall the right call? That's an open question among analysts. The manifold strikes created the torch. They were the mechanism of maximum cascade effect. But they also created the fire that complicated damage assessment and potentially masked the extent of the direct turbine hall damage from immediate satellite observation. A different targeting approach, concentrated entirely on the compressor units, might have achieved the operational shutdown without the sustained torch. But the torch achieved something the silent shutdown could not. It created an undeniable, visible, internationally documented event that could not be explained away as an equipment malfunction. The torch was a statement. Whether that statement was worth the additional complexity in damage assessment is a legitimate tactical question. Could the Russians have prevented this strike? With the air defense posture they had in place at the time, probably not completely. They might have intercepted additional drones with better coverage. They might have detected the formation earlier with more comprehensive low-altitude radar coverage. But the fundamental vulnerability, the existence of high-value, unhardened infrastructure nodes in territory assumed to be safe rear area, was not going to be solved by additional Panzer systems at individual sites. Solving it requires either hardening the infrastructure itself, which is enormously expensive and largely impractical for existing pipeline systems, or establishing comprehensive low-altitude air defense across vast swaths of Russian territory, which is also enormously expensive and represents a strategic resource competition that Russia is losing. What would you have done differently if you were commanding this operation? Would you have committed a larger strike package to guarantee the destruction of all 12 units? Would you have accepted the risk of the Su-30SM patrol and held a higher altitude flight profile for better battery margin? Would you have targeted the upstream emergency shutdown valves as a primary objective to prevent the rapid isolation that might have limited the torch duration? These are the questions that military planners ask after every operation, and the answers shape the next one. Subscribe to Ukraine Radar, because we break down the battles that textbooks will study for decades. Not just the explosions, the decisions, the trade-offs, the moments where preparation, intelligence, and tactical judgment converge, or fail to converge, and the outcome of an operation hangs on a 4-minute window while two fighters sweep a patrol corridor 18 kilometers away. Real tactics, real consequences. Ukraine Radar. The compressor station is cold and dark now. The turbine hall, or what remains of it, is open to the sky where the roof collapsed. The manifold piping that carried billions of cubic meters of gas is shattered and scorched. The emergency shutdown valves that finally choked off the fuel supply to the torch stand closed, frozen in the position that ended the fire on day 6. Silent. The pipeline upstream is repressurized, but the flow takes a different route now, rerouted through alternative pathways at reduced capacity. The downstream industrial complex is recalibrating to a new supply reality. The engineers who will eventually rebuild this facility, if it is ever rebuilt, will work from a design philosophy that must now account for the possibility of precision air attack from a direction that used to be called safe. The torch is gone, but the scorch marks remain. Silent reminders that modern warfare punishes infrastructure assumptions without mercy. That rear area security is not a given. That the distance between the front line and the pipeline that sustains the forces fighting on it is, in the age of long-range precision UAVs, no longer a meaningful measure of protection. Stay vigilant.